Greetings and welcome to the lecture series on equations and inequalities in two variables. In this lecture 3.7, we'll discuss variations. So what does it mean to have a variation? Well, a variation is a relationship between two or more variables. And relationships can come in many different forms. One is direct, another is indirect, and another is jointly. And you can have a combination of those variations within the same formula or equation. So let's discuss direct variation. When we say y varies directly with the variable x, there's a relationship that we can write, y equals kx. And k is a very, very important component to this equation. So k is a non-zero constant. If it was 0, then y would just equal 0. So it's called the constant of variation, also the proportionality constant. And occasionally you'll see that there's a proportional relationship between the variables. So that's why we can also call it the proportionality constant. Wording is going to be really important here because you're going to have to decipher a real-life situation and try and put it into a math equation to be able to work the math. When it is stated that y varies directly with x, that's the same thing as that it is directionally proportional to x. Well, let's take a look at several different wording and see how it would look like algebraically. Y varies directly with x. Well, there's a direct relationship. Therefore, it's going to be y equals k times x. Remember, when we vary directly with something, we have this proportionality constant, this constant of variation that's involved. So it's not just y equals x, it's y equals k times x. S varies directly with the square of t. This time, s varies directly, not with just t, but the square of t. So s equals k times t squared. Y is directly proportional to the cube of z. Y equals k z cubed. And then u is directly proportional to the square root of v. So here are your two variables, u and v, and therefore it is the square root of v that's involved, not just v. And you can think of it as u equals k times the square root of v. So what do we do with this? Well, with any equation that has variables, if we are given two of the variables, we can solve for the third one. If we're not given enough information to solve, we need to take it into steps. And with these variation problems, we're going to generally do two steps. The first step is generally finding the k value when you're given a y and an x value. So you'll get that constant, and that constant is a constant. It will never change. No matter what your x and y is, for the situation, k will never change. So your first step, you're given a y, you're given an x, and you're going to solve for k. The second step, you're going to be given a value of x or a value of y, and you have to solve for that third variable. But you're only given one variable. That's because in the first step, you solved for k. Right? That k does not change for this situation. So y varies directly with x. If y is 15 when x is 5, find y when x is 7. Okay. Here's the first part we need to decipher. Y varies directly with x. The second part is we're going to start working with the numbers. So first step, let's find k. Find k when y is 15 and x is 5. Well, if y varies directly with x, then y equals kx. We're now given y, we're given x. We can solve for k. 15 equals k times 5, divide each side by 5, k equals 3. This constant does not change. Even though our x's and y's will change, our constant will not change. So step 2 is we're going to find y when k is 3 and x is 7. Okay, we're going to plug that in. Y equals kx. Y equals k is 3, x is 7, so y would equal 21. There's this relationship between y and x, but it is affected by the value of k. So first step is to find k. Second step is to find what they're looking for. All right, let's take an actual application problem. A skydiver jumps from a plane. That is, the distance of the skydiver when he falls is directly proportional to the square of the time he has been falling until he reaches terminal velocity. If the skydiver falls 64 feet in the first 2 seconds of the jump, then how far will he have fallen in 3.5 seconds? All right, so it didn't look like they gave us much information, but let's decipher what's going on here. Skydiver jumps from the plane. Yeah, that's nice to know, but it doesn't have any effect on our math. The distance of the skydiver that's falling is directly proportional to the square of time. If we call the distance d and time t, distance is directly proportional to the square of time. Therefore, d equals k t squared. Now, till he reaches terminal velocity, we're not going to worry about terminal velocity right now. If the skydiver falls 64 feet in 2 seconds, then how far will he jump in 3.5 seconds? Well, first I need to use the information of the 64 feet and the 2 seconds and solve for k. Then we can use k and the 3.5 seconds to find the feet he has fallen. All right, d is 64, t is 2. Plug it into our equation. 64 equals k times 2 squared. 2 squared is 4. So 64 equals k times 4. Divide each side by 4. K will equal 16. Now that we know k, we can figure out how far he has fallen in the 3.5 seconds. So let's plug it back in. When k is 16 and t is 3.5, d equals k times t squared will equal 16 times 3.5 squared. 3.5 squared is 12.25. So 16 times 12.25 is 196. And distance was measured in feet, so in 3.5 seconds, he would have fallen 196 feet. Now, what does that look like? What does this relationship look like? Well, we can plug in some values after certain time lengths, and I just did it in second increments. So 0 seconds, of course, he's fallen 0 feet. In 1 second, he's fallen 16 feet. 2 seconds, 64 feet. 3 is 144. And I literally just plugged it in to t would equal 1, k is 16. T would equal 2, k is 16. K never changes. And then after 3 seconds, he's fallen 144 feet. 4 seconds, 256 feet. 5 seconds, 400 feet. And if we graph this, we can see that it's a nice steady curve to the length of time that he has fallen and the feet he has fallen. Of course, it makes sense that the more time he's in the sky, the further he falls until he finally reaches reaches the ground. So how long would it take him to fall 256 feet? According to the ground, at 256 feet, that would be 4 seconds. Second type of relationship or variation is the inverse variation. That means, if you think about it, if one of the variables goes up, the other must go down. It's doing the opposite. So we have a relationship between the number of minutes, t, that it takes to run a mile and the average speed. So if we describe that relationship as S is t equals 60 minutes over the time it takes to run that mile, we have this interesting relationship. So I'm just going to put some inputs in, some outputs in. So when t is 4, 60 divided by 4 is 15. When t is 6, 60 divided by 6 is 10, so on and so forth. So 8 and 7.5. When t is 10, the output is 6, in essence 6 miles per hour. If it takes 12 minutes and you're running 5 miles per hour, if it takes you 14 minutes, you're running 4.3 miles per hour. So the faster that you run that mile, the faster speed you have. But as the time increases, the speed is decreasing. If we graphed this, you can see that there is a steady curve going downward. And that makes sense. If I run slow, then it's going to take more time to run that mile. So there is an inverse relationship. As time increases, speed decreases. If time decreases, speed increases. So we can say, because of this opposite relationship, so when one decreases, the other increases, and when one increases, the other decreases, we say that the variable s, which is the speed, is inversely proportional to the variable t. In this case, the constant of proportionality, k, is 60. So s of t equals k over t. The other way we can think about it is s of t equals k times 1 over t, the reciprocal of t. Either way, the math will work out. So let's take a look at the language and what it would look like algebraically. All right, y is inversely proportional to x. Y equals k over x. S varies inversely with the square of t. S equals k over t squared. Okay, the square of t, t squared. Y is inversely proportional to x to the fourth. Y equals k over x to the fourth. And z varies inversely with the cube root of t. Z equals k over the cube root of t. Right? Inversely, if you think of what is the inverse of t, it is the reciprocal. You can think of it as that as well. Hence the k over 1 over t, which is the reciprocal of t. So let's take a peek at an example. The volume of a gas is inversely proportional to the pressure of the gas on the container. Right? So think of this. I don't have a jar close to me, but let's see. Let's say you have a bottle and you put some gas in it, and then you pressurize it. You push it down with a plunger. Think of those French coffee makers where you put the coffee grinds in there and then you push it down. Then everything below that stopper gets crushed, so the volume gets smaller. So the more that you push down on the plunger, the less volume you have, but the pressure is greater than the volume. So the more pressure, the volume decreases. That's an inverse relationship. Therefore, it's going to be one of those situations where it's going to be y equals k over x in some sense. It's an inverse proportionality. Okay, if the pressure of 48 pounds per square inch corresponds to a volume of 50 cubic feet, what pressure is needed to produce a volume of 100 cubic feet? First thing we have to do is figure out what our equation is. If the volume of the gas is inversely proportional to the pressure of the gas, then we can say that volume V equals K times, because it's over, K over P. And I'm just going to use V for volume, P for pressure. So V equals K over P, inversely proportional. Now we're given the pressure at 48 pounds per square inch corresponds to a volume of 50 cubic feet. So pressure is 48, volume is 50. Plug it into our equation to find K. Once we do that, 50 equals K all over 48. Multiply each side by 48, and we get 2400 equals K. Some of these numbers for K might look a little odd to you, but trust your math. All right, now we want to find what pressure is needed for a volume of 100 feet. Well, given K is now 2400 and volume is 100, we're going to find P. So 100 equals 2400 over P. Multiply both sides by P. 100P equals 2400. Divide each side by 100. P equals 24. 24 watts though. Always go back to your problem and see what measurement it is. 24 pounds per square inch. So what does that look like on a graph? It's an inverse relationship. So as volume is high and pressure is low, we start up here on the graph. As pressure increases, the volume decreases, and we have this inverse relationship. Let's talk about our third type of variation, which is joint variation. And then from there, we're going to start combining these. And you got to, when you're reading these problems, be very careful about the language. Okay, joint variation. If y varies directly with two variables, we'll just call them x and z, then we say y varies jointly with x and z. How do we write that up? Y equals k times x times z. Okay. Varies directly with two variables jointly. So we multiply them all together. All right, so let's look at a couple of these. Y varies jointly with x and z. We saw that. Y equals kxz. Z varies jointly with r and the square of s. Okay, the square of s will be s squared. R is just r. So if z varies jointly with r and at the square of s, x equals krs squared. Okay. V is directly proportional to t and inversely proportional to p. All right. So directly proportional to t, that would be the V equals kt, and inversely proportional to p. Therefore, all over p. No, we don't have another k involved. It is the one single k. This relationship is with both t and p. And if you want to think about this in terms of the inverse of p would be 1 over p, and if the relationship is joint, then it's t times 1 over p. V equals k t 1 over p, which in essence is the same thing. Oops, sorry about that. Okay, kt 1 over p. And indeed, if we simplified that, it would be v equals kt all over p. All right, let's look at a few more, or at least one more. F varies jointly with m1 and m2, and inversely with the square of r. Okay, so let's take the first part. F varies jointly with m1 and m2. That's going to be F equals k m1 m2, and inversely with the square of r. Well, inversely means that it's in the denominator, therefore all over r squared. Let's take a problem, an example. Y varies jointly with x and the square of z. When x is 5 and z is 3, y is 180. Find y when x is 2 and z is 4. The first sentence, y varies jointly with x and the square of z, we're going to decipher our equation. Okay. Y equals k times x times y squared. The second, when x is 5 and z is 3, y is 180. X equals 5, z equals 3, y equals 180. Plug all of these in, all three of these variables, to find what k's value is. 180 equals k times 5 times 3 squared. 3 squared is 9, so it's going to be 180 equals k times 5 times 9. 5 times 9 is 45. 180 equals k times 45. Divide each side by 45. K will equal 4. K will equal 4 for all circumstances of x, y, and z for this problem. Now that we know k is 4, we can move on to find y when x is 2 and z is 4. Same equation, y equals kxz squared. X is 2, z is 4, k is 4 from what we found in the first step. Plug that all in. Y equals 4 times 2 times 4 squared. Well, 4 squared is 16, so 4 times 2 times 16 is 128. So y equals 128 when x equals 2 and z equals 4. Physics. Physics uses inverse, joint, and direct relationships all the time. Physics is a big one for this. So let's talk about electricity. And the resistance of a cable is directly proportional to its length and inversely proportional to the square of the diameter. Okay? You're given that information. In physics, you'll start figuring all these things out by testing, but and lab work. But you're given this information. So before I give you what I'm going to call R for the resistance, L for length, and D for diameter, before I start giving you the numbers, let's figure out what our equation is. The resistance, R, of a cable is directly proportional to its length, L, and inversely proportional to the square of the diameter, that would be D squared. Since the first part is directly proportional, that would be similar to R equals KL. But now we have to add the inverse proportionality of the square of the diameter. So altogether, R equals KL over D squared. Now, let me give you some more information. If a 100-foot long cable that has a 1/2 inch diameter has the resistance of 0.2 ohms, what will be the resistance of a cable that's 200 feet length and a diameter of 1/4 inch? Okay, let's take the first part of that. If a 100-foot length cable has a 1/2 inch diameter, it has the resistance of 0.2 ohms. All right, let's plug that into R equals KL over D squared, where R is 0.2 ohms, the length is 100 feet, and the diameter is 0.05 inches. Okay, when we plug that in, 0.2 equals k times 100 all over 0.5 squared. 0.5 squared is 0.25, so 0.2 equals 100k all over 0.25. Easier for me to see the k on the right, so I just swapped places. All right, multiply each side by 0.25, so 0.2 times 0.25 equals 100k. 0.2 times 0.25 is going to be 0.05 equals 100k. Divide each side by 100. K will equal 0.0005. Trust your math on this. I know these numbers will look a little strange, but k is a very small number, not exceptionally small, but a small number of 0.0005. Now that we know what k is, we want to find out what the resistance of the cable when it's 200 feet in length with a diameter of 1/4 of an inch. Plugging 200 for L, 200 for L, 0.25 for D, and 0.0005 for K, we will get R equals 0.0005 times 200 all over 0.25 squared. When you do this math, the resistance will be 1.6 ohms. Ohms is measurement of resistance. So that's it for this lecture. I suggest practicing with these, and to get the language into the math, I think, is the hardest part. The math you've dealt with for a long time. It's just translating the English over to the math. So until next time, be seeing you.